what's going on in these collections of atoms? Well, we said that for molecules and solids, one way to think about this often we say, well, atoms combine to form molecules and solids, but I think it's better to think in terms of its nuclei and electrons. And the nuclei let's think of which kind of contributions the nuclei and the electrons are making. If I think in terms of the mass of a molecule, or the mass of a solid, I brought in a solid piece of metal. It's a solid. Okay. Anyway, we'll talk about electrons in a minute. If I think of nuclei versus electrons, where's the mass?
Nuclei.
In the nuclei, right? How much the mass in the nuclei?
Most.
99.9 something %, right? So the mass is here. How large is the nuclei?
Tiny, tiny.
The nuclei are really tiny. Right, if you look at the distributions for the nuclei are really tiny. Electrons give molecules their bulk, or their size. Right, so it's the electron distributions that are filling everything up. But they don't contribute much in the way of mass. Now we picked out some kind of representative molecules. What do we say maybe is the best molecule to think in terms of here? H2, right? Everybody's favorite molecule. So H2, if we apply this idea to it, how many nuclei do we have? 2. How complicated are those nuclei? They're just protons. How many electrons do we have? 2. And how much? Well, let's draw a picture. So I've got a nucleus. I've got a nucleus. And we said that there's going to be some electron distribution, just like in the individual atoms. But this time the electron distribution is going to get shared in some way between the nuclei. So that was kind of our picture of what's going on inside a molecule like this. What kind of energy do I have in my molecule? Well, I've got kinetic energies, right? I've got kinetic energies of the electrons, and I've got kinetic energies of the protons too. So I can have kinetic energies here, kinetic energies here, and I got all the potential energies of all the interactions. And what we typically do is we divide this into the electrons are going to have different molecular quantum states in these molecules the same way they did in atoms. Now it's a more complicated problem because we got at least 2 nuclei that we have to deal with in figuring out what these quantum states are going to look like. We talked about this a little bit on Thursday. Today we want to pick up with some other kinds of energies that we didn't have before. We didn't see these in atoms. And these are rotational energies and vibrational energies. If this is my H2 molecule, what does a rotation mean? What does it mean to say a molecule is rotating? Oh, and I want to write these as quantum states too. So we're going to get quantum states with rotation and quantum states with vibration. But let's just think about what rotation would be. Back in Physics 4a, we introduced the idea of rotational kinetic energies, right? So we said 1/2 I omega squared, where I is A rotational inertia, and omega is what?
Angular speed.
Yeah, it's angular velocity or angular speed. There's an alternate way we could look at this. We could rewrite this, not in terms of omega, but we could rewrite it in terms of angular momentum. And if I do that, I end up with 1/2 angular momentum squared over I. Now we did the same thing when we were looking at the Schrodinger equation. What's an analogous set of equations for translational kinetic energy? Translational kinetic energy, classical translational kinetic energy, 4A kind of stuff. What would I write down for kinetic energy here? 1/2 mv squared. And then we said, you know, in quantum physics, V is not as well defined as what? We said actually it's easier to work in terms of momentum. Momentum, we had definitions for momentum operators. So we're doing kind of the same thing in rotational terms that we did in translational. What we're doing is, we wrote down the 1/2 I omega squared. He said, but you know, I'd like to do that in terms of some kind of a conserved quantity, right? Angular momentum is a conserved quantity. It plays an important role, kind of the same way that linear momentum does. Let's try thinking of the kinetic energies in terms of this. All right. How many different axes could we have kinetic energies around? Here's my H2 molecule. Here's an axis right there that I could imagine. Here's a second axis that's perpendicular. And then I can have a third axis that comes in and out of the board. If I have an axis right here, do I have a kind of a meaningful rotational inertia around that point? You go, yeah, around that axis, what would the rotational inertia be given by? Anybody remember rotational inertia? How is that done?
MR squared.
Yeah. So it's always going to be some kind of a mass times some kind of dimension squared. And yeah, if I've got a concentrated mass like I do with these nuclei, so the nuclei are going to be like point masses. Right? I can treat that as all the mass is concentrated at one point. And yeah, for those kind of situations, I can just say it's mr squared. So in this case, I'm going to have a rotational inertia contribution from here and from here. We can say, yeah, rotations around this, I could follow this formula and put something in for a rotational inertia. What happens in a perpendicular direction here? So yeah, that would give me rotational inertia too, rotating around this axis. This axis isn't so well defined. Right here, I've got an axis that goes right through the nuclei. We really don't have much in the way of rotational inertia to speak of. So we really have two different directions that we can keep track of rotations here for our rotational kinetic energies. Now if we write this as 1/2 L squared over a rotational inertia, are we going to end up quantizing this? And by quantizing, I'm saying, are we going to have certain energy states that are allowed and some energy states that are not? Okay, back when we were looking at electrons in hydrogen, were those energies quantized?
Yeah.
Yeah, they were. What quantized them? You guys remember? Yeah, there were energy levels, but what gave us the energy levels? There were boundary conditions, right, on the wave function that gave us only certain wave patterns would fit the boundary conditions. And we're actually running into kind of the same thing here. Remember back then we went in and we quantized angular momentum. So this has actually been done. We quantized angular momentum and said that it always shows up as L plus 1 times h bar squared. So we can use the same arguments as before. If angular momentum is still being quantized, we should end up with a set of rotational states based on the amounts of rotational momentum or angular momentum that are possible. Okay. So what we want to do now is, I used the green marker. You guys were supposed to tell, you might be not there. Use the green marker again.
Wasn't that just on the other board?
What was that?
Wasn't it on
In the other room?
That it was worse?
I don't know. It's, yeah, the greens have been giving me problems lately. They never did in the past. What have we done?
White's the new green,
White, green.
ecologically friendly one.
Yeah, that's
It's
right.
harder to get off.
Lulled me into a sense of complacency.
Yeah, ripped off. One thing you buy those things for is so they erase.
That's right. Non-erasable markers. All right. Well, now that we've got that erased, we'll move back over here. And okay, rotational inertia. We got to go in and take care of this. How much rotational inertia do I have in this molecule? In my H2 molecule? We can actually show that the rotational inertia can be written as what's called the reduced mass. Maybe we'll get a chance to go in and see where this comes from. So what we had was, there's an R1 on this side, there's an R2 on this side. I get a rotational inertia contribution here, rotational inertia contribution here. But I don't want to leave it in terms of R1 and R2. Right? What I'd like to do is write it in terms of R, where R is the distance between the two nuclei, right? So it's our internuclear distance. What's that also called? In chemistry, it's called what? It's called bond length. Right, what's the distance between the two nuclei? That's my bond length. So that's better. You want to be able to work with this in terms of something that's familiar of the properties of the molecule. And we can do that if we use this combination of reduced mass. Okay. So reduced mass, that's a mu. This is M1 times M2 over M1 plus M2. And combining all those pieces together allows us to go in and calculate the rotational inertia. Okay, so we're just about ready to kind of map out what these rotational energy states are going to look like. One last thing, how general is this diagram we just did? How general is this analysis? We started out saying we were looking at H2, but maybe we could generalize it to other molecules as long as what? As long as they're diatomic. Yeah, as long as these molecules are diatomic, this should still work. Diatomic would mean what?
Two atoms.
Two atoms or two nuclei. So we got two nuclei surrounded by some number of electrons. Okay, what are some other examples of diatomic molecules?
O2.
N2, O2, carbon monoxide, you know, the H2 that we've already listed. So we've got a good number of these. In fact, you know, 99% of the air in this room is diatomic, right? So, all right. So each of these is going to have a different value of rotational inertia, okay? And that's going to determine what the energies look like for rotational quantum states. So let's do a chart. What are the allowed values for my angular momentum quantum number? 0, 1, 2. Yeah, so I go through all the integers. So we'll do 0, 1, 2, 3, etc. What am I going to get for energies at each of those quantum states? Well, here's my, okay, I gotta go back. This is a K for kinetic energy, right? And that's what the rotational energies are, they're kinetic. But those are going to get switched back over and they're going to show up as energy L, or they will also be written as energy of rotation. So when you look through the book, it can go back to being a big E. All right, what happens if I put a 0 in for L? I get 0. That one's not so hard. So I'm actually allowed to have no rotational energy at all. The lowest quantum state, the ground state, is no rotation. And it's a spherically symmetric wave function. Okay. Equally likely to be at any orientation. Right? The molecule can be oriented anywhere you want, equally likely. No rotational energy. What about when L is 1? Well, that looks like it's going to leave me with h bar squared over I. So let me write these down. E naught is equal to 0. E1 is equal to h bar squared over the rotational inertia. What's energy state 2 going to look like? And 3. Let's get at least this many. So this is 2 times 3. The 2's will cancel. That'll give me 3. This is going to be 3 h bar squared over I. And then one more. 3 times 4 is 12 is 6. Is that it? So this h bar squared over I keeps showing up. And we could do an energy diagram. Now this is energy of rotation. It's kinetic energy. It's always going to be positive. So we're not dealing with those negative energies that we saw back when there were potential energies around. So I can start right off with 0. So I could start off with 0 energy here. Well, let me write it this way. And then I'm going to move up to this next state. I guess we'll just do the line. And this one was coming in at h bar squared over I. All right, I want to keep this diagram going. I want to make sure it's scaled properly. Where do I put E2? Yeah, it's got to be 3 times higher, right? So if I take a look at how much of a gap I had right here, I got to go here, here. E2 is going to be up here. Yeah, and then the next one's got to be where? Uh-oh. It fits, right? What's happening to the spacing between my states? Yeah, it's increasing. Okay. All right, let's say that we have a transition. The molecule is in state number 1, it transitions to state 0. What happens? What's going to happen with that energy? Yeah, we're going to release energy as what? Photon. So we're going to end up with photons being radiated, photons being generated from these transitions between quantum states. And looks like the energy of my photon, if we transition from here to here, the energy of the photon, E1 minus E0, okay, E0. Do I want to write an electron on that line? Why not?
This is a rotation.
Yeah, these are rotations. It's different. So, and this is an issue that I always wonder about this. What we're looking at is an entire molecule. So it's not that one particle has gone from one quantum state to another. It's a big, complicated molecule, right? It could be an N2 or an O2 molecule with lots of protons and neutrons and electrons inside there. It's the entire molecule that has transitioned from a certain amount of rotational kinetic energy to a lower amount of rotational kinetic energy. So, kind of interesting. You can take these composite structures that seem really complicated, and they've got quantum states too, at that higher complexity level. So yeah, we can follow the same ideas that we did before in figuring out how much energy the photons are going to come off with. All right, let's look at an example. So, carbon monoxide. Carbon monoxide is a good example of a diatomic molecule. And we could look up some data on carbon monoxide. So we could take a sample of carbon monoxide into the lab, we could send through a spectrum of light, and we could see which light gets absorbed. Okay. Now, if I start with carbon monoxide molecules that, for whatever reason, if they're in the ground state, and they absorb a photon, this time we'll have photons coming in, I could have a transition from the ground state into an excited state for my carbon monoxide. And some experimental data says that this actually occurs, and the wavelength of the photons that we see is at 2.61 millimeters. And this is for the L equals 1 to L equals 0 transition. So if I'm transitioning back and forth between L equals 1, L equals 0, I'm going from L equals 1 to L equals 0, I'm generating a photon, right? What happens in order to have the process go in the opposite direction? Yeah, there we'd have to absorb a photon, right, to take in that energy. But this is the number that shows up. So given that, how much of a gap is there in energy between state 0 and state 1? HC over, yeah, right. So we'll do this as HC over lambda. That's going to give me, wait, if we do this, what were the units we had for HC? Yeah, these were like EV nanometers, but now what are the wavelengths like? Yeah, it's like 2.6 million nanometers. How much energy are these transitions? Not much. They're really tiny energies. So I've got relatively long wavelengths compared with what we've seen before. And that says the energies are going to be really tiny. These are small transitions. The energy I ended up with was 4.76. 10 to the minus 4 EV. And that's pretty typical. When you look at rotational energies in molecules, the energy gaps between the successive quantum states are pretty small. This could be in the region that we might think of this as being microwave, right? Which makes me think, well, I've got a microwave generator at home, which is like, I think it's the best thing we've ever invented. I would say we wouldn't need anything that we were cooking with. But microwave ovens are doing what? We're generating a bunch of photons with this sort of energy to them. Down in this, 10 to the minus 4th EV, that's going to be enough energy to do what to your food? Yeah, it's going to make some of the molecules rotate. Okay, so you're going to end up exciting the molecules into a rotational state. So, would we expect that to be dangerous? Microwave photons, would they be dangerous? Compared with X-rays. Nah, because the X-rays, each photon has so much energy, right? How much energy do these individual photons have? It's like nothing, right? It's not going to take your molecules apart. Now, it could be dangerous at what?
Long time.
At lots of them, yeah. So don't take the door off the front and bypass the switch or whatever. So if you have a lot of them, it can turn out to just be enough energy to just kind of, it could become dangerous. But photon by photon, these are pretty low energy. All right, let's see. What could we find out about our carbon monoxide molecules? And I would like to take this and find out what is the bond length. That might be interesting. We could find out what is the bond length in carbon monoxide. And we could do that by just analyzing the spectrum of light. that it absorbs in the microwave region. So looking in the microwave region, we pick up, this is the energy of the photon. Let's see if we're going to get a bond length. What do we need to calculate here? We need to work back through some of these equations. Hope we didn't erase anything that was too important here. So, what is the difference in energy between these two states? Yeah, so we've got the energy of the photon is equal to E1 minus E0. And that looks like it's going to be h bar squared over I. That would actually let me go in and calculate the rotational inertia of a carbon monoxide molecule. So if we do this as h bar squared over the energy of my photon, that gives 1.45 10 to the minus 46 kilograms meters squared. I'm a little nervous. That's a really small number. Does that seem too small?
No.
So why not?
Kilograms.
Yeah, it's in meters and it's in kilograms. And the carbon monoxide molecules are going to have little tiny masses. And they're going to have tiny bond lengths to them. So let's see if we can sort this out. I would be equal to the reduced mass times the bond length. There it is. So to get the bond length, I need the rotational inertia, and I need a reduced mass. So apparently I have to be able to figure out a reduced mass for a carbon monoxide molecule. How would that be done? Well, what are the two masses that we're dealing with? Yeah, right. So it's back to this idea of, well, it's really just the two nuclei that we're paying attention to. And one of them has a mass of 12, and one has a mass of, assuming what?
Assuming that they're
Assuming that they're the most common isotopes. So this is saying, oh wait, this is going to have an isotope effect to it. Different isotopes are going to have different properties in terms of their energy states, but the masses will be different. Right? But let's take the most common ones. Let's say that we have something that's 12 atomic mass units and 16 atomic mass units. And then in the denominator, we're going to get 12 plus 16. That's going to be 28 atomic mass units. Okay, how many sig figs do I have here? What's the mass of carbon 12? 12.000. See, that's the definition of a time. Yeah. So this is actually 12.0. I just didn't write all the zeros in, right? And if I look at the oxygen isotope, most of these isotopes, you're getting more than just one. You're getting more than two significant figures. You've got, yeah, there's some zeros out here, right? This is like 15.999 something, right? Anyway, so we really can't keep like 3 sig figs from this. I ended up with 6.86 atomic mass units. Now these are atomic mass units. I better get that written too. How do I convert from atomic mass units into kilograms? Let's see. Yeah, it turns out that 1 gram is equal to Avogadro's number of atomic mass units. You want to bet or something like that, right? What's that? So 1 gram is Avogadro's number of atomic mass units, but we're working in kilograms. How many would that be? Well, that would be a kilomole of atomic mass units. And this often gets turned around the other way. You know, 1 atomic mass unit is like 1.67, is that it? 10 to the minus 27 kilograms. So we want to turn this around and get the reduced mass back in terms of kilograms. minus 26. All right, this is it. It's the final calculation here. How am I going to calculate that log rate? Well, I can take this rotational inertia, which was 1.45, 10 to the minus 46. You know, I got to watch units here. You know, units become important in this calculation. 1.14, 10 to the minus 26 kilograms. Taking square roots is important too. All right, what happens in terms of units? Kilograms canceled. I'm left with meters. And the meters that I ended up with were 1.13 times 10 to the minus 10. So is that, should I write that as millimeters? Should I write it as micrometers, nanometers? How about picometers? Yeah, picometers actually would be good. I noticed Wikipedia now is just standard on picometers. When you look up compounds that have bond lengths in picos, which I really like. So 113 picometers. Is that the right number? I don't know. Anybody have a textbook? So yeah, that's a pretty reasonable sort of number. Right. What can we compare this to? I guess the only other thing we look at is kind of the Bohr radius, right? What was the Bohr radius? It's like 50 picometers. Now hydrogen's going to be like the smallest thing out there, right? So this seems entirely plausible. And in fact, you can do these measurements in other ways, and that's about what we did. So that's kind of interesting, right? That you can take this idea of rotational energy quantization. You can predict kind of what energy photons will get absorbed or generated by these molecules. And then you can go in and do the measurements, run the numbers through, and actually work back and find something out about your molecule. You know, how big is this molecule going to be? It's going to be this big, because that's what we measured in the lab. All right. Questions on any of this? All right. So we said with our diatomic molecule, maybe I'll move it out to the side here. We draw it. That seems pretty good. So we were able to go in and look at rotational energies and identify rotational quantum states. I say the rotation energies look like L plus 1, h bar squared over 2I, where L is some integer value, 0 or some positive integer. Then we want to move on and take a look at vibration. So we had listed those both as possible energies. We're going to stick with our diatomics. I like the diatomics because why? They're as easy as we're going to get, right? We're not going to get any easier than the diatomics. So how do we want to model vibrational motion? Vibrational motion in a molecule, a diatomics like this.
Spring.
We can think of this as kind of a spring in a mass system. Okay, now there's not really little tiny springs, at least we don't think they're little tiny springs, inside these diatomic molecules. But what we do have is we have offsetting effects. So what is it that is drawing the molecule together? What's tending to collapse the molecule down? We got, yeah, the electromagnetic forces, right? So I've got these negative charges and these positive charges, and overall the electromagnetic force is tending to collapse into everything. Why doesn't the molecule just collapse?
Electromagnetic force. Same force.
Yeah. So what we looked at before is the electrons need their space. What would happen if I took all these electrons and I collapsed the molecule down so the electrons were in a much smaller region? What would have to happen to the kinetic
Did
energy?
you say you have to increase it?
Kinetic energy would have to go really high. So I'm getting this lowering in potential energy, but I'm getting this increase in kinetic energy of the electrons. So if the electrons can't collapse any further, if we've kind of packed the electrons into the region they're comfortable with, then the protons are going to end up repelling each other within that negatively charged region. And we'll hit some kind of an equilibrium. Okay. What would happen if I turned up the electromagnetic force constant? I go, you know, the electromagnetic force constant in nature, I really want it to be a lot stronger than it currently is. Let's turn it up. What would happen?
Small molecule.
Well, yeah, we could collapse all this molecule down a little farther, right? The forces then would tend to drop farther, but at some other point we'd hit an equilibrium. Okay, so kind of the size of molecules and atoms depends on this balance between whatever the electromagnetic forces look like, what the electromagnetic force constant is like, versus quantum effects, Planck's constant. How much room do electrons need? How much space do they need? All right. Okay, I'm going to say one more thing, and then we're going to stop for a minute. So here's what I want to think about here. I want to think about this as vibration. Vibrational quantum states would come from imagining the nuclei inside this diatomic molecule oscillating back and forth inside this negative distribution of electrons. So I got this background of negative electrons, and the protons are oscillating back and forth, and that gives me vibrational energy in the molecule. And I couldn't do that with one atom, right? One atom by itself, rotation is not really well defined. One atom by itself, the nucleus can't really oscillate back and forth, right? So you need a pair of nuclei at least to start to see these vibrational quantum states show up. All right, so that's my picture, and I'll say this is an amplitude of vibration for this, and there's going to be, K here is going to be an effective spring constant because there's not really springs in there. And if we look at the energy, if we look at the potential energy as a function of R, actually total energy, I guess we should say. If we look at the energy as a function of R here, at first everything's drawn together by electromagnetic effects, and then we hit this wall of quantum effects showing up, and the molecule does not comfortably collapse. And so we end up with an equilibrium separation. So here is my R naught. That's how far the nuclei are separated at equilibrium, and then we're getting oscillations around the equilibrium point. All right, what's the shape of that energy curve? Near the bottom. If I start at the bottom, and I look in this direction and look back in that direction, what does it look like? Think calculus 3D. Maybe 3D, right? You guys do expansions? We can take a function like this and we can expand it around a particular point. Well, if I'm in a region where the molecules are close to equilibrium distance, and that's what I've got in my diatomic, right? In this diatomic molecule, the nuclei are pretty close to their equilibrium separation, and then they got a little bit of vibration around them. So I'm in this region, and this lower region can always be approximated. Let me write the energy this way. I'm going to write the energy as some bond energy. The bond energy is the difference between the 0 point down to this negative region. And then we can add on to that plus 1/2 K. So what we've got here is we've got this bond energy, which is negative. That's kind of holding everything together. And then on top of that, if we do an expansion around this point, the first derivative is going to go to 0, right? Why does the first derivative go to 0? Because we're looking at the equilibrium separation. If I'm looking at equilibrium separation, I'm at the point where the potential energy is as low as possible. The first derivative in the expansion goes away. What am I left with? Well, I'm left with the second derivative, which actually is what k is. So k here is like, second derivative with respect to r evaluated at r is equal to r0. And that is equivalent to a spring constant. If I was back thinking of, falling back in 4a, spring with a couple of masses attached to the end of it. And that's how we're going to analyze the vibrational energy. Okay. I'm going to stop there for today because we have to do a class evaluation here, and I'm going to stop so we have time before the communications class comes in. So I will leave. Patty Sy is here from College of Alameda. And who wants to do this?
I can use it.
Okay, thank you. I'll get out of here so you guys can get started.
Oh, that's fine. So can I just use one of your markers
Yes.
and I'll bring it over to the lab?
Yeah.
So, as you know, every single instructor is evaluated regularly, and this is Dr. Nicole's turn. I'm going to pass the forms out, then I will put on the whiteboard. I'll see you in a couple minutes.
Okay.
I'll put on the whiteboard the stuff to fill in the top. The one thing that's really confusing is that number 1 is the best score. So it's like, if you could pass these. Number 5 is the worst score. So it's usually 5 out of 5 is the best. But on this particular survey, it's the opposite. So if you could just take one, pass it to your, that way, that's your right. Here we go. And then I also have pencils. So does anybody need a pencil? All right, here, hang on a moment.